Hi folks, this is Mariam Tahan from the Office of the CTO again in Red Hat, and just continuing on a series of demos we were doing where we firstly showed how to migrate a DPDK application from using the vanilla DPDK PMDs using AFXDP under DPDK without making any changes to your DPDK application. Then we showed how you can launch this application or service in the Kubernetes cluster, originally using the SROV device plugin and the host device CNI, but this implied that you had to provide your pod with privileges in order to use AFXDP under DPDK. And then we showed how you can also migrate to using the AFXDP device plugin, as well as the AFXDP CNI, to launch a DPDK AFXDP pod that is unprivileged inside Kubernetes. And within the context of the AFXDP device plugin here and the AFXDP CNI, we actually did all the bpf program management on our own. Additionally, when the DPDK pod came up, it actually connected back to the AFXDP device plugin over a Unix main socket and performed a handshake in order to retrieve the XSKMap file descriptor that it needed to create the AFXDP socket. So we wanted to migrate from managing the bpf programs within the context of the AFXDP device plugin and the CNI for a couple of reasons. Firstly, every time we wanted to update our container image, there is a dependency on that image having some version of BPF supported, and basically BPF support varies widely from base image to base image, which was creating all of these sort of complexities whenever we were trying to update our container images. Additionally, we had to statically link the BPF library into the CNI binary, which was also, not a very flexible option. And lastly, we didn't have really a lot of flexibility in terms of the BPF programs that we were able to use, or we wouldn't be able to make things configurable without essentially compiling the BPF program and storing the BPF bytecode inside the AFXDP device plugin container image itself. So for all of those reasons, we decided to migrate to use bpfman or bpf manager, and essentially we are now able to communicate with bpfman via its client APIs in order to request it load the BPF program on the NetDev interfaces as well as unload them. We communicate with bpfman as well to understand where it is pinning the XSKMap, and once we have a pinned XSKMap, we can mount that into the context of the DPDK pod without having to do any additional handshakes. At the moment, the XSKMap is mounted into the pod via host path volume mount. However, in the next version of the integration with bpfman, we'll actually be migrating to leverage the CSI plugin inside bpfman to allow us to actually pin the XSKMap within the context of the pod itself, so there won't be a reflected mount point on the host side itself. Everything will be within the context of the pod. Okay, so let's go ahead and check that the BPF pods are all up and running inside our cluster. And we can see here we have the bpfd daemon, we have the bpfd operator. So bpfman went through a name change. Originally it was called bpfd, and then it changed its name to bpfman. So we're working with bpfd version 0.3.0, which is why we're still seeing our pods being referenced as bpfd within our cluster. We also have Multis running here. So let's go ahead and start up the AFXDP, or deploy the AFXDP device plugin. So let's just check the AFXDP device plugin pod is running. Check the logs there. We can see that it started the AFXDP device plugin, and that essentially it is ready to service any device requests on the host. Okay, so let's go ahead and try and deploy the UPF, the OMEC UPF, using the AFXDP device plugin with map pinning and bpfman. We can see that the pod is starting. We can see that essentially, if we look at the logs here within the context of the pod, we can see it calling the init internals under the AFXDP PMD. It's trying to use a pinned map, which it's trying to retrieve from this path inside the context of the container. And it looks like that it's successfully retrieving the file descriptor for the XSK map for both interfaces that are allocated to the UPF. But if we check the logs again for the AFXDP device plugin, we should probably see it try to communicate with bpfman. Yeah, so at this stage here in the AFXDP device plugin, essentially it creates an XDP program resource, and we'll check that out in a second, and pushes it up to kubelet, which eventually gets pulled down by bpfman and serviced by bpfman, and essentially it also retrieves the location of the map from bpfman for that XDP program. So let's try and see what that looks like. So we can see if we try and get the new XDP programs.bpfd.dev CRDs. There's 2 of them created, and they're loaded on the interfaces that we see here. Okay, so at this stage, let's just start loading the PDRs and other rules into the OMEC UPF. And let's also forward the the port 8000 from the UPF pod to the local host, so that we can essentially have a look at the pipeline. So here we can see the pipeline, and looks the same as the other demos that we showed here. So let's go ahead and just check that the rules are installing, and we can see the number of rules at least incrementing in terms of PDRs, QERs, var lookups as well, and so on. So once all of the rules load, we're going to pass some traffic through and check that everything still works as expected. Okay, so now that the PDRs are all installed, let's go ahead and pass some traffic through the UPF. And we can see traffic coming in through the interface, passing through the PDR lookups, GTPO decap, QER lookups, and essentially going all the way through to the routing lookup and out the next interface. Okay, so at this stage, let's go ahead and stop the traffic. Let's step back to the Kubernetes cluster and see that the XTP programs are still there, and we're going to delete the OMEC UPF and then just check that the XTP programs are indeed deleted as part of the interaction between the AFXTP device plugin and bpfman. So I'm just going to go ahead and delete the UPF. So if we try and see XTP programs, we can see that they're deleted. If we see the logs for the AFXTP device plugin, we can also see that it essentially deletes the XTP program resources for the two interfaces. And the last thing I would like to show is the AFXTP device plugin daemon set definition, or the spec, to essentially showcase that we have a lot more flexibility with the AFXTP device plugin being integrated with bpfman. So this is the AFXTP daemon set specification or definition for deploying with bpfd integration. We essentially enable the bpfd client support in the device plugin. And the other thing I just wanted to highlight is that the bytecode is actually built into container images, which is pretty flexible because we can essentially define what container image we want to use on a per pool basis, and what program even within the context of the bytecode we want to use for a particular interface, which gives us quite a bit more flexibility in terms of program definition than we had before with the AFXTP device plugin itself managing our BPF programs in total. And that's really it. Thank you very much for your time, and hopefully the next demo will be able to show full integration with the CSI support in bpfman. And that's it for now. Thank you.